when we discussed stress, we discussed about sign convention. Similarly, we are going to discuss about sign convention for normal strain. It looks very obvious, but there is a subtle point here. The sign convention for strain goes in line with the sign convention for stress. Let us see how does it reflect here. Now, if you take a solid object and apply a tensile stress is pulling away, and according to our sign convention, tensile stress are positive, okay, on a positive phase along positive axis. So, they represent positive stresses. When you apply a tensile stress, what happens to the length? The length will increase, and what will be the normal strain? It will be a positive value, okay, and that is what we are seeing here. Normal strain was defined this way: epsilon n limit q tending to p, delta s tending to 0, the change in length delta s star minus delta s by delta s. Okay. Now, as we have seen now, if you subject a object to a tensile stresses are positive, because on a positive x phase the force is along positive x axis, negative x phase force is along negative x direction, and of course tensile forces are positive, and that results in an expansion. So, delta s star will be larger than delta s, you will result in a positive normal strain. So, we can conclude that positive normal stress, tensile stress produces positive normal strain. Negative normal stress, what does it mean? Suppose you apply a compressive stress, the length will decrease. When length decreases, delta s star will be less than delta s, this will be a negative value. So, negative normal stress also called as compressive stress produces negative normal strain, just like positive normal stress produced a positive normal strain. So, the sign we could have defined, for example, delta s minus delta s star, okay, but we are defined as, of course, final length minus initial length, which looks more logical anyway, but the sign convention associated with the strain goes in line with that for the stress as well. Okay. Like to mention here this we could have left at change in length alone, okay, just like we left at change in angle, but change in length is not normalized. That is why to normalize, express as a fraction, we divide by original length, otherwise it is just, it could be 2 centimeter, 5 centimeter, it is not normalized. To normalize, we divide by the original length and get a normalized expression. Of course, that is not required for the shear strain, it is just a change in angle. Okay. So, now let us see the sign convention for shear strain. Okay. What is shown here is a stress element with only shear stresses, all of them in the positive sense. What does it mean? On a positive x phase, force along positive y direction, positive y phase, force along positive x axis. In the negative phase, on a negative x phase, the direction of force along negative y axis, on a negative y phase, force along negative x axis. Now, this combination of forces, combination of direction of forces represents all of them in a positive shear stress. Okay. What does it mean? If you take an object, your shear stresses will, the forces will act in this direction, and here they will act in this direction. What will happen? It will make the object to shear in this way, that is what is shown here, which means the angle which was originally 90 degrees will now decrease, and we know that from the definition of shear strain, that the decrease in angle results in a positive shear strain. Okay. So, positive shear stress results in a positive shear strain. Okay. I will just repeat it. We are considering shown a stress element here, 2D stress element with all the shear stresses in the positive sense. When you represent in positive sense, the forces are such a way, if you have a cube, they act in this way and here in this way. So, they make the cube such a way that this angle which was originally 90 degrees will now reduce, and that is what is shown here. According to our definition of shear strain, the shear strain is 90 degrees minus the final angle, and the final angle is reduced. So, the shear strain is positive. So, positive shear stresses result in positive shear strain, and that is what is shown here as well. The stresses are shown in the positive sense, and that is what this indicates, positive shear stress. What does it result in? Positive shear strain. Okay. Now, and that is the first statement we make here, positive shear stress produces positive shear strain, just of course decrease in angle or acute angle. Okay. Now, let us discuss the reverse condition, and that is what is shown here. Now, all the shear stresses are negative here. Why? On a positive phase the force is along negative direction, on a negative phase the force is along positive direction. Similarly, here also on a positive phase force along negative direction, on a negative phase force along positive direction. So, these the action of forces according to this direction are all negative shear stresses. So, you have a cube and they act in this direction. So, now what will happen? This angle will increase, it will become an obtuse angle. What will happen if you have an obtuse angle? You have pi by 2, this is an obtuse angle. So, you have a negative shear strain. So, negative shear stress results in negative shear strain. So, okay, that is the statement. Next statement, negative shear stress produces negative shear strain or increase in angle or obtuse angle. The important point in these two slides is that the sign convention for stress and strain are related. The sign convention is such a way that what we have adopted is that positive stresses result in positive strain, be it normal or shear. Okay. That is the conclusion from these two slides. Okay. Let us take an example of stretching of a wire. This example is to illustrate the calculation of local strain. You would have done the same example. You are given a wire, you are given the initial length, you will be given the final length, you will find difference in length divided by original length. You would have calculated strain, that gives the average strain over the entire length. But now we are going to apply our expression, our definition of local normal strain, and going to see how local strain varies locally along the length of the wire. Okay, that is the example. Let us read this. A wire of finite length L initially lying in the x direction, So, initially your wire is along the x axis, is stretched along a rigid track which is a parabola. So, you are stretching it along this track, which is a parabola, which is given as y of x equal to b x squared. All points of the wire displaced in the y direction only. What does it mean? If you have a point here, it will move straight away in the vertical direction only. If a point here, it moves in the vertical direction only. That is for simplicity. All points of the wire displace in the y direction only. Compute the strain at all points of the wire. That is the difference between what you already know and what we are discussing now. Okay. So, let us do that. Let us start with the definition of normal strain. Epsilon n p is equal to change in length by original length, of course limit q tending to b delta s tending to 0. Now, we are considering the wire which is lying originally along the x axis. So, our delta s star is the final length, initial length is delta x because along the x axis, similarly initial length is delta x, and instead of delta s tending to 0 I write as delta x tends to 0, and instead of n I write as epsilon x x. We said for the normal strain of line elements along x axis are denoted as epsilon x, in the two subscript notation they are epsilon x x, and that is what is shown here. Taken a small line element along the wire in the original configuration, that has become delta s star in the deformed configuration. This is the undeformed configuration or initial state of wire. This curve, the parabola, is the final configuration of the wire or the deformed configuration. We are told that every point gets displaced only vertically. So, that is why this vertical line shows this point moves vertically up, this point moves vertically up. So, what happens, this length delta x becomes this length delta s star. So, our definition is delta s star, the final length minus the original length divided by original length in the limit of delta x tending to 0. Why do you do that? We get a point value of the normal strain, and the nomenclature is epsilon xx. Okay. We will have to evaluate this formula, we will have to evaluate this expression, that is what we are going to do now. Now, this portion is shown here, and because we are considering a small segment of the wire, you can approximate this delta s star to be a straight line, and the x axis distance delta x, let us call the y axis distance as delta y. Okay. So, delta x is the that we already seen, a length of infinitesimal segment, we are taking a small segment of wire in the initial position, okay, and delta s star, as we have discussed, the deformed length of segment, okay, of the wire when stretched, which is called as the final configuration. Okay. So, from this figure we can write delta s star as square root of delta x squared plus delta y squared. Let us divide by delta x squared and take out delta x, and we get this expression. Now, we substitute this expression in this definition of normal strain, epsilon xx is equal to limit delta x tending to 0. Instead of delta s star, I substitute this expression minus delta x by delta x, you can cancel out and delta x, okay, and that leaves us limit delta x tending to 0 and then minus 1, okay, because delta x can be cancelled out. Now, we take limit delta x tending to 0, which means that this will become dy by dx the whole squared. So, our expression for epsilon xx is root of 1 plus dy by dx the whole squared and then minus 1. Okay. Now, let us proceed further. We are given the expression for y, which has y equal to bx squared. Okay. We will have to just differentiate that to get dy by dx, substitute in the expression root of 1 plus 4 b squared x squared minus 1, okay, and this expression gives you the local strain, that gives you the strain at every point along the wire. That is the difference between what you already learned and extra information from this. Okay. Of course, the strain, remember, the strain varies along the length of the wire, it is not constant, it is a function of x, okay, and at x equal to 0 this becomes epsilon xx equal to 0. So, that if you take a small point at a, there is no change in length at all, it is just there, okay, and maximum strain, where does it happen? If you see here, this segment CD has become C star D star. So, the maximum strain occurs at x equal to L, okay, and if you want to simplify, for example, if Bx is very smaller than 1, then you can approximate this using the binomial theorem by this expression 1 plus 4 b squared x squared into 1 by 2 will give you 1 plus 2 b squared x squared and then subtract minus 1. So, to a quick approximation, the strain, the normal strain varies quadratically with the position or with x, okay. Strain is a quadratic function of x. So, only one main concept in this example, we evaluated normal strain locally in a wire that is being stretched. Okay. We will take an example for evaluation of the shear strain. Now, what is shown here is a plate, and you are given the undeformed configuration, you are given the deformed configuration, initial state, final state. Okay. Always remember, in all these cases a force is applied and it continue to apply, okay, and then it undergoes deformation. Okay. Original configurations are P, C and then A, the original points are P, C and A. The point P has not moved, it has remained at P star. So, P equal to P star, A has moved to A star and C has moved to C star. Okay. Now, the vertical displacement of A, this length is given as 0.24 L. The dimensions are given in terms of L, L could be taken as unity as well. So, the length is 3 L, the width is 2 L, okay, and this displacement is 0.24 L and this displacement is 0.24 L. Okay. The vertical displacement of A is 0.24 L, the horizontal displacement of C is 0.24 L. Okay. Now, let us read the problem. Points A and C of a rectangular plate shown in figure. So, you should imagine a taken a plate and then mark some points at the end points. Displace two points A star and C star along the x and y axis, respectively, so that the rectangle is deformed a parallelogram. If you look at P star, C star, A star, the dashed line is a parallelogram. Okay. Lines that are initially parallel to the axis remain parallel lines. What does it mean? Initially you would have had lines like this, okay. You would have had lines like this, lines parallel to the x and y axis. Now, in the deformed configuration they remain parallel, which means that you have lines like this. Why this statement is required? Just to simplify the problem, saying that the shear strain is same throughout the plate. You will not find shear strain at every point in the plane. If you are finding one value of shear strain, the change in angle, that is applicable throughout the plate. That is why lines parallel to the axis, they remain parallel in the final configuration as well. Okay. So, let us evaluate the shear strain. Let us start with the definition of shear strain. We are considering point P, the two line segments are along x axis and along y axis. So, we replace gamma n t with gamma xy and pi by 2, and what is the angle? The r star, p star, q star, if you look at our original diagram, it represents the angle between the two line elements in the final configuration. What is the corresponding angle in this diagram? It is C star, P star, A star. Is it okay? That is a final angle. So, pi by 2 is the original angle, C P A, that is the angle 90 degrees, minus the final angle is C star, P star, A star. Now, what is to express in terms of what is given to us? We will express the difference between 90 and this angle as sum of these two small angles. Is it okay? Instead of this 90 minus this angle, we will represent that as sum of these two small angles, and that is what is written here. The difference in the angle is equal to sum of A star P star A, that is this angle, plus C star P star C, that is this angle, okay, which are very small values. Now, based on the dimensions given, the displacements given, we can evaluate gamma xy. What is the angle A star P star A? It is just tan inverse of 0.24 by 3, L of course cancels out. Now, for the other angle, it is tan inverse of 0.24 L divided by 2 L, L cancels out. Now, if you evaluate gamma xy, you will get a value of 0.1993, specifically written for 4 decimals. We will understand why do we do that. This is the exact value of the shear strain. Now, if you assume gamma xy is less than 1, a small value, if you assume it so, what happens? These angles become very small, very small. Angles between sides of, see, when you remember we discussed rigid body and then deformable body. You can quickly approximate bodies to be rigid, but we are discussing deformable bodies, that is we are discussing about strain, etc. And I told you, if you apply megapascal of force per area, the change in length will be a very small value of millimeter or 10 power minus order of 10 power minus 6 meters, it will be in terms of microns. Similarly, if you apply megapascal of let us say shearing force, the angle change will also be very small. Okay. That is why we are discussing the assumption of gamma xy being less than 1, which means that these angles will be very small. So, assuming gamma xy less than 1, angles between sides of parallelogram and x and y directions are small. What are the angles? These angles are very small. Now, we know that for alpha less than 1, any angle less than 1, tan alpha is equal to alpha, which means that alpha is equal to tan inverse of alpha. So, instead of taking tan inverse, I can straight away use 0.24 by 3, similarly here 0.24 by 2. Let us do that and see what is the value. So, gamma xy is 0.24 by 3 plus 0.24 by 2, you get a value of 0.2000. Now, this is the exact value. Why? We have taken tan inverse. This is an approximate value. Why? We have not taken tan inverse, but look at the error, a very small error of 0.35% is introduced. We will be using as we go along only this value, it is almost there, almost accurate, only a small error is introduced, and we will be following this second approach as we go along. Just to illustrate numerically why do we do that, you will understand later on. Okay. So, we have found exact value of shear strain, an approximate value, but that is a very good approximation for the exact value. Okay. Now, the question mentioned that the all parallel lines remain parallel after deformation, we have illustrated in the previous slide. So, angle changes, we have calculated angle changes for the boundary between the two boundaries of the plate, x boundary and y boundary. It is applicable at any point inside the plate. So, the angle changes are same at all points in the plate. That is why if this is not given, then we cannot come to that conclusion. That is why that line was mentioned, because it is a very simple example, angle changes are same at all points in the plate. Okay. And which means that the shear strain is constant throughout the plate. Okay. Angle changes are nothing but shear strain.